Wait, what? No.
Alright, so this unit can be broken up into 3 parts, is what I've been telling my classroom. The first unit is Young modulus. This unit, the first part is Young modulus. I said it was over there. So, Young modulus, no Young modulus. And then the second part is why things sink, why things don't sink. No pressure, density, and the last part is going to be Bernoulli's and the continuity equation. So let's get started with problem number 1. So with your group, go ahead and answer what is Young's modulus. The Young's modulus equation. And keep in mind, tomorrow during the test, you'll have an equation sheet. So what is Young modulus equation? With your group. Brandon told me, why am I asking you, what is the equation? And I told him, because I want you to already have that equation fresh in your mind going to a test, know where to find it on the equation sheet. So, Young's modulus, what is Young's modulus is if you apply stress to something, that thing is going to strain. It's going to do. So, what's the equation for stress? Otherwise known as maybe pressure? Yeah. Force over area. And then strain?
Change in L over L initial L.
Yeah, and let's look at these variables. What does the change in L mean?
The change in
Like how much it's strained?
Yeah, like how much it stretch or compress.
compression.
And then L is what?
The original.
Yeah, the original length. So go ahead with your group. Go ahead and take a few minutes and go ahead and solve number 1. Bone has a Young's modulus of 1.8 times 10 to the 8th pascals. Under compression, it can withstand a stress of 1.7 times 10 to the 8 pascals before breaking. Assume that a femur is 4.4 meters long. Calculate the amount of compression this bone can withstand. So go ahead and work that out with your group.
SCP femur breakers.
So what is the just modulus number 1? Oh, so this would basically go so. It just turned on.
Did you get it fully chargeable?
I did not.
You literally just look for a green one.
What happened, Mr. Jonathan? What upset you?
I'm just this crap about it.
Did you ever send me a book? I'm cleaning that up and we did.
This is kind of like finding avenues is my special talent.
So, sorry about that delay. So, start out the equation. I mean, write down the numbers they give you. Like, write down your givens. What are you looking for? And select your equation. So, in this problem, they tell us.
Bless you.
I hope you said bless you at home. So, Bone has a Young's modulus of 1.8 times 10 pascals. That goes there. It can withstand the stress about 1.7 times 10 to the 8 pascal. So where do I put that?
Yeah, this one.
On the force
No.
or on the area?
Just literally just in a
All of it, yeah. So they tell us how much was it?
1.7 times 10 to the 8.
Times 10 to the 8. And then bone is 0.44 meters long. That's going to be right here. And we're looking for how much it's going to compress. So at this point, it becomes like an algebra problem. I go ahead and divide 1.7 e to the 8. I divide that by 1.8 e to the 10th. And I end up getting 0.00944. Is that what you guys got when you guys divided
Yeah.
this by that? I get change of vowel, 0.44. And how do I cancel that 0.44? I'm gonna multiply times both sides, so times 0.44. And my answer ends up being, change in L is going to be 0.004156 meters. So let's talk about the lab that we did. We did a lab on Young's modulus where we had to find the length of the Young's modulus. So in that lab, what did we use as our force
Wait, which lab?
Oh,
on the lab for the Young modulus.
the little weights, the new
Oh,
ones.
Yeah.
the wheels, yeah.
We use the weight pulling on that rope thing. I don't know how to describe that. What did we use as the area?
The area, wasn't it like, it was a cylinder, wasn't it?
Yeah, we can think of the rope as a cylinder. So what did we use as the area?
I don't know what the number was.
Fire screen.
It was pi r squared. Because here's the rope in our lab. And that force is being applied on that area of the rope. There's no force being applied over here on the side, it's just straight down. So for the area, we use pi r squared in our lab. And then we knew the original length, and then we measured how much it changed, and from there we were able to find the Young's modulus. So think back to the lab, and then also know the Young's modulus, know all the parts of it, know what all of it stands for. Questions on number 1? All right. So on number 2, go ahead and talk to your person around you. Feel free to look through your notes. But there's an equation, and if you don't know the equation, that's okay. Well, it's not okay, but I mean, for right now, you should know the relationship. What is the relationship between depth and pressure? And then what is the equation? So go ahead and talk with your group amongst that.
I don't know. I probably have to put it on.
So, all right, coming back to it. What do you know about depth and pressure? When we did that FET simulation in class, what did we learn about? What's up?
Isn't it the increased depth, the more pressure?
Yeah, all that matters is the shape of it doesn't matter. The only thing that matters is the depth. So the more depth there is, the more pressure there is. So, for example, let's say I have a pool, and one of my pools, I have 2 pools actually. I'm super rich like that. So I have 2 pools. So one of my pools is a kiddie pool, and it only has 1 foot of water. And then I have another pool, and that pool has 5 feet of water. Like I said, I'm super rich.
Right.
So which of my pools has a greater pressure? Like those walls are containing more pressure. Why the 5 feet? Yeah, there's more water. So if I were to put that much water into the little one,
It would overflow.
not only would, let's say it was like magical water, and it wouldn't overflow, it still wouldn't be able to take it because that's way too much pressure for that little thing. That's a lot of depth. So the more depth, the more pressure that thing has. So it has to be, so more pressure, you have to be really strong to withstand it. So going back to this problem, calculate the pressure of an object when it is 200 meters below the ocean of water. The density of water is 10.25. So, and I'm sorry, as soon as I read it, I remembered I didn't answer the question. So what is the equation that relates density and depth and pressure?
Is it initial pressure plus density plus gravity times height? Or
Yeah, that's the long version of it, but the simpler version is, in order to find the pressure at that specific point, it's going to be density, which is that little, I'm going to put pressure for this one.
So what Greek letter is it supposed to be?
Rho.
gently down the stream?
So gravity and then H. So it's the last part of Bernoulli's. It's the last part of Bernoulli's.
Sounds familiar.
So go ahead and solve number 2. That one should take you like a minute.
What does it say next to it?
I put pressure, like, so you don't confuse that here with the other one.
Calculate the pressure of object fuels.
Yeah, I like it more than the way that So, what did we end up getting for this? So 1025,
20 million.
1025
20 million. 90
times
million.
9.8
Yeah, I got the same thing, Joe.
Yeah.
times 2000. And that ends up being 2.0 times 10 to the 10th power. Now, John said something really interesting. That's not actually the pressure of that object right there. You still need to add the pressure of the atmosphere. So it's the pressure becomes the atmosphere plus that right there. Pressure equals pressure of the atmosphere plus that. Questions on number 2. And they'll tell you in the problems, they've been telling you, if you've been doing your quest, they tell you yeah, I know. They tell you the atmospheric pressure is this, or they might tell you neglect the atmospheric pressure. Like, they'll tell you like what that is. So just the important part is knowing the relationship with the depth. So number 3 is, what is buoyancy, and how do you know if an object will sink, float in place, or actually float up? So go ahead and take, oh wait, what's up?
When they ask you to find the pressure, do you always add up the atmospheric pressure to the number that you got?
Yeah.
You always-
So let's say the atmospheric pressure, Mr. Rios, do you know the atmospheric pressure like at sea level?
At sea level, my memory? No.
Yeah, me neither.
1 point.
It's
Oh, one,
it's
three.
1 atmosphere, but I don't know how much it is in pascals.
Pascals is 1.013 times 10 to the fifth power.
All right. Good job. So, yeah, you always will add the atmospheric pressure in.
Is that going to be given?
If it's necessary, they will give it to you because it's part of the problem. So,
I know, sorry.
but what I want you guys, the part that I want you guys to practice is the depth kind of thing, and that more depth means more pressure. So that thing is holding on to more pressure, needs to be like stronger and things like that. That's it. No more question number 2. So number 3, what is buoyancy, and how do you know if an object will float or sink or float up? So go ahead and talk about that. Ultimately, only one thing matters. For this problem, but I'm going to show
Like I covered the force of the object.
It's like good at school and shit.
It's actually like
Middle school was like, do you have them here?
Doesn't matter, no A, usually A is always good.
If they use
I was gonna come for just a paper, but I was like, oh, that's fun.
So, Justin just brought up something really important that I've been mentioning all year. There's different E's in the calculator, and they stand for different things. The E that I'm talking about, that means times 10, is the E, the double E next to the letter A. If you try using the E to the X, you're talking about exponential growth right there. So that's not that little E, it's the 2 double E's at the bottom.
What about us for like base calculus?
There's a button that says times 10 to the something power. So, alright, what is buoyancy? How did we define buoyancy in class?
Something floats or not.
Well,
It's a measurement. Like, yeah.
buoyancy is the force that pushes you up.
Pushing down, or when something is, it's like, yeah.
It's
Remember
low
the
to the
example,
normal
like,
force.
the example we got was like with the beach ball, when you push it down, there's an equal force pushing down.
If it floats, yeah. So,
No, I don't.
let's go with Derek's idea. So, if a ball is floating in water, what is the force that's pushing it down? It's weight.
It's much.
And what is the force that's pushing it up? The force up is, I'm gonna misspell this word, so I'm sorry. On there, I spelled it right.
It's U before O.
What?
It's U before O.
This is
All right.
physics and English, John.
So, when an object floats, this is the relationship that we need to know. Buoyancy, the equation for buoyancy is density, gravity, times volume. And that's equal to, when an object floats, it's equal to mg. And if we do like a little bit of math right here, we can rewrite mg. Mg can be rewritten as that. And that comes from the density equation. Like we established this relationship in class where density is equal to mass over volume. So I can rewrite this to be density times volume equals mass. And that's what I did right here. And what do you notice with that we can do right here?
Cancel the cancel the G's, right?
Yeah, we can cancel the G, and we can also cancel the volume. The volume. These volumes are the same. We can know that these volumes are the same because of Archimedes' principle. However much volume this object takes up is going to be equal to the same volume that is displaced. So if these cancel out, then what is the only thing that matters if an object floats or not? The density is the only thing that determines if an object floats. So if the more dense that you are, the more density of that object, what do I know is gonna sink. So the more dense things will go to the bottom, and then the less dense things will go to the top. That's all that really matters, the density. And I wanted to show you where it came from. When buoyancy is bigger, that object will shoot up. And when that weight, when the density of the object is bigger, then the weight is bigger, so it's going to sink to the bottom. But ultimately what matters is the density.
So you cancel out the G's and the B's and you just density?
Yeah, the only thing that is left over is density. So kind of like that problem on your quest where it was the mercury, the water, and the steel ball, and they ask you like, if you put them all together, how do they look? Well, the water was the most dense thing, and that's why it went to the bottom. And then they tell you the steel ball is less dense than the water, but more dense than the mercury, and that's why it was in the middle. And then the mercury is the less dense of all of them, and that's why it was at the top layer. So, questions on number 3? So let's talk about Bernoulli's equation. So Bernoulli's equation can be thought of as the conservation of energy. So go ahead and take a brief moment with your group again, because I want you guys to know these equations. Write down Bernoulli's equation down. Like, what is Bernoulli's equation?
It's a string, yes, no, it's a string.
What is Bernoulli's law?
Oh, yeah.
But the volume is
Any more? Alright. You'll handle those two. So, Bernoulli's is about relating different parts of a tube to another part. And you can think of it as like conservation of energy. So what is Bernoulli's equation? P1 plus 1/2
Okay, no.
density
Oh, I know which one.
V squared
The energy.
plus density gravity height. And what do I know about Bernoulli's in one area of a tube versus Bernoulli's in another area of the tube? Yeah, that doesn't change. P1 plus 1/2 density V2 plus rho GH. So we have this problem right here. What happens to the pressure in a straight pipe as the area of the pipe gets smaller? So, oh my gosh, you guys already we're just talking about it now?
Yep, yeah.
Yes,
Alright.
no, we're discussing it for numbers, so we're done with that.
All right, no more discussing groups. We're sort of done with that. So let's look about what assumptions can I make about this right here?
They cancel.
Exactly,
Why do they cancel?
because they're literally the same.
The height is a
Yeah, the height's not changing. Gravity's the same for both of them. It's important to establish that this idea that the heights are the same. On number 18 on your homework, the height changed, so you couldn't cancel them, but did I mention it was a straight pipe where the height didn't change? That's important. So over here, it's kind of like that. So when the pipe gets narrower, what's going to change in that pipe?
It's
Well,
velocity.
The velocity.
the speed's going to change. And what's going to happen to the speed over here?
Be
It's going to get bigger. So that pressure got bigger. But what do I know about these two things?
they're equal. So
Yeah, they have-
something else has to get bigger.
They have to be equal to each other. So the pressure over here is 100, and this is 100 over here, and this is 150. I know that that's gonna stay the same. But if my velocity went up, what happened to my pressure?
It went down. Down has to get smaller.
Yeah.
If one gets bigger, the other one has to get smaller.
So no Bernoulli's, and know that if there's particles right here, if there's particles inside this tube, due to the pressure change, those particles on this side would actually be larger. Something important to know. So let's say there's some gas particles inside. Because of the change in pressure, those particles would actually be larger. Questions on Bernoulli's? No? All right.
The velocity gets larger, the pressure gets smaller,
Well, these two sides need to be equal to each other. So if this goes up to let's say 200, we know that this part cancels out. That didn't change at all. So in order to keep things equal, this number has to also change. And in order to keep it balanced, we saw that change. Yeah, I probably shouldn't have used 200 because then that's 0. But yeah, there's. So on number 5, when an object floats, what can we say about the buoyancy and the weight?
They're equal. The buoyancy is big.
Well, I mean, like, if let's just say it's just floating there, what can we say?
They're equal, so they're in equilibrium.
The buoyancy is greater than the weight.
Well, it's not being pushed up, it's just floating there. Yeah, the buoyancy is going to be equal to your buoyancy is going to be equal to your weight.
So the density of the water and the density of the object, right?
Yeah.
So,
Number 6. Questions on number 5 or 4? So go ahead. What I want you guys to do now is we're going to do the continuity equation. So a pipe has a radius of 0.5 meters, and 10 meters later the radius changes to 0.35 meters. The speed of the water is 7 meters at the narrow part. How fast is the water flowing at the first end of the pipe? Sorry, people that are watching at home. There's a typo right there. So we have, once again, similar scenario. We have a big pipe, and then it's getting narrower. So what equation would I write down to set this up? A1 V1 equals A2 V2. And what's up?
What was the typo?
The typo was I forgot to put at the first end of the pipe. I'm asking about how fast is it going at the beginning? Because when it narrows, that's when they tell you the speed. So what does this A stand for? Area. And when we're dealing with pipes, what is the area? Pi r squared. So pi r squared V1 equals pi r squared V2. And this is why it's important to work with variables, because it's when you put in just numbers, it's hard to see them cancel. When you put in letters, you make the problem easier for yourself, because what do you see that I can do? I mean, it ends up I can't cancel the squares for any, because those squares are actually, those r's are actually different. But the pi ultimately doesn't matter. So it just becomes R2 V1 equals V2, or if you just want to calculate what pi r squared is for the area, that's fine. It's up to you. But go ahead and solve this one. Where the heck is pi over here?
No, because that's no, it's 7.
Oh, shit.
Squared times 7. Yeah, so 1 squared times 7 is equal to 35. Yeah, because 25 squared is
That makes sense. Down.
1.5 square, 1.5, okay, 7.
I think the X is right.
The narrow part, the smaller part.
Yeah.
Narrow and small, so you can multiply by the smaller.
Are you guys getting 3.63? 3 point what? 3.43?
Oh, shoot.
Is that what everyone else is getting and I just made a mistake? Alright. So, how do you set this one up? So, it'll be pi, and the first radius is 0.5 squared. We don't know that velocity. We know this radius is 0.35 squared, and they tell us that velocity right there. So you multiply all of this out, and then you divide by this side, and you guys seem to be end up getting 3.43.
What? What are you getting?
Oh, there we go. That's what it did.
Oh, maybe I did something wrong. Never mind, yeah. Listen to him.
Is that right? I'm like, that's what I got too. So when I plugged it into the calculator, I did it with the pies. I didn't cancel out the pies, but I just wanted to show you that you could for those people that are want to be more efficient. This is the continuity equation. What questions do you guys have on number 6? None? Alright, let's go ahead and do number 8. We're back to Bernoulli's. So, on number, I'm gonna do, that way you can do the last two. So I'm gonna do number 8, and then Mr. Rios is gonna come up and do number 9, because he has a much more efficient way than my way. So, and then that's it. And then he was also gonna do 7. Oh, simmer down, God.
You didn't say anything about 7.
Water flows. This must be so annoying to watch on YouTube. So, water flows at a speed of 5.6 meters per second through a horizontal pipe of diameter 3.5 centimeters. The gauge pressure at P1 of the water in pipe 1 is 1.6 atmospheres. A short segment of the pipe is constricted to a smaller diameter of 2.2 centimeters. What is the gauge pressure? So go ahead and with your group, go ahead and solve this one, please. You are going to be reusing Bernoulli's.
Oh yeah?
What? Yeah, so it's like a
Look at that.
I'm not asking something. I know how to actually know.
Okay.
Technology that he has access to.
I need to know.
Okay, you just act like Quest doesn't do online. Just look up a site to
Today?
Well, I was going to
Yeah, that one over there, 24.
Right now?
Yes.
What happened? You were doing so good.
You guys have no reason to put up the game.
I don't know.
Yeah, that's fine.
You guys. Honestly, it's a level.
Lost my what?
I went to the doctor's. The lady said that she knew him invented. Old lady. I want to say old. I want to say old lady.
Wait, how did we come up with this?
I think I've never had it.
What's 3.5 divided by 2? What's
Dude,
2?
I've met her too, I swear.
1.75?
Yeah?
Yeah.
She took my weight and all that other stuff. She was like,
She was like, I have, she's like,
something like that. I was like,
Say it over to the old
and he was like, yo, he was like, all that down here.
nah, and I was like, ooh. She's like, yeah, that's
Sister.
she's a nurse.
Oh my, oh I know, yeah, I know.
Yeah, she's a nurse. Oh yeah, what's wrong with sister? Will this be on the desk? Honestly? I mean, I'm going to do it. I'm just gonna have to remember this like I did with the ladder problem.
You don't know how to do it?
I know how to do it.
Oh, you look at this
I don't remember the answer. I'm solving it right now.
I thought you had it solved.
Relax, right?
Mister,
I did, this is the one that I did to everyone.
We get it. You solved everyone. You didn't charge anyone.
I'm going to now.
Sean.
For real.
Are you seriously finding that shit easier?
I legit just
Hear what he said. Just say it again.
your body accidentally. Bro, why am I getting this song in my playlist right now? Like, this is not it.
Ryan.
Is it right or not?
I don't know. What you get for the second? I don't know. 14 velocity. 14 from
Okay, this
169.
ain't right, okay.
That's the other velocity.
No.
I just didn't want to do it. And you guys end up getting 14.169 for the other velocity.
Well, I got 14.17.
Yeah, I got 14.176.
Bro, what?
Like that's what I'm doing right now. Yeah. And so the same thing with the ladder.
I look like my thing.
You said every ball guy is going
Bro, that's
But the problem is, the pressure has to be.
I caught my dad
All right. We are simmer back, and simmer down. So we are doing Bernoulli's right here, and in Bernoulli's, they're giving us. It's gonna be P1 plus 1/2 density velocity squared plus density gravity height, and we know that Bernoulli's is gonna be equal on both sides. So let's pause for a moment right here. What do I know about what can I do right here that I know based on the drawing that they gave us?
They have the same height.
They have the same height, so what can I start canceling out?
Canceling out the PGH.
I can cancel this whole part, that pressure right there. I just wanted to mention, that is pressure, look. Density, gravity, height. That's another. So that's why when that changes, something else is gonna change. So we ended up getting P1 plus 1/2 density, P1, P2 plus 1/2 density, velocity squared. Now, please take a moment to look away from your papers and just look over here for this. You too. Maximize this screen. Shut off that Netflix and look at the screen. So, how could I solve? How could I solve for the difference in? How could I solve for the difference in pressures? What would I subtract?
The right portion. The 1/2 PV squared.
Yeah, I would subtract this 1/2 PV squared to this side, and I end up with P1 equals P2 minus and then what would I do? Because I want to find the difference. What's up?
We already have P1.
Oh, I know. This is just like, I'm going to go back to the problem, Carla. I just want you to know that, because what I want you guys to understand, the problems that I give you on this review, they're not like, if you came to the last review, you know that they're just to prepare you. They're not going to be exactly like the same as the test.
Yes, they were. The last review was okay.
So what I'm trying to get you to understand is that if you set up the equation, you're able to manipulate it to solve for whatever you want. Like right now, I want to solve for the difference in pressures. And the difference is, well, like a subtraction. So how do I find, if I want to solve the difference in these two pressures, what other thing do I need to do?
We need to subtract.
Subtract what? Yeah, I'm going to subtract the second pressure. So P1 minus P2 is equal to 1/2 So all I did was I subtracted from both sides. These canceled out. But what I do to one side, I do to the other. So you guys can solve for all these different. If you know this equation and you understand what they're asking you to solve, you can manipulate this equation to solve for whatever you want. Like one of the problems on the quest, they wanted you to solve for the difference in velocity. So in that one, you had to kind of do the opposite, subtract these values until you ended up with v minus v, the difference in velocities. But ultimately, it all comes back to Bernoulli's and knowing how to set it up. So let's go back to this problem right here. Can I erase this right here?
No, absolutely not. No.
This guy's copying down stuff.
First time in my life.
And then we're almost done. Mr. Rios is gonna do the last two problems with you. And we're actually gonna change problem number 7. Like I said, it was hard to find problems for this one. That's why it took me a long time. Can I erase it now?
Yeah, sure.
It's like, yeah, sure, whatever, sir. Got what I needed. I hate you now. See ya. So, now let's go ahead and plug in. So the things that we know, they gave us the pressure over here. What was that pressure? 1.6. 1.6 atmospheres plus 1/2 the density of water If you've been doing your quest, you know that density was 1,000. And then they give me the first velocity. What was it? 5.6 squared equals, I don't know that, that's what I'm looking for. 1/2, 1,000. And the problem for this problem comes in where I don't know that other velocity. So what do I need to do? I need to do the continuity equation. So I'm gonna do that right here on the side. A1 V1 equals A2 V2. So it's pi r squared. Velocity 1 equals pi r squared. Velocity 2, so it's the pi. Half of the radius, what did you guys tell me it was? 1.75.
Yeah, that's right.
And then that velocity, you guys told me it was 5.6.
Don't you convert it to meters?
Wait, it's in centimeters.
It's in centimeters?
Yes.
So that'll be point
0.175.
0.0175. On that test, any conversions that you'll need, like always, we'll give them to you. We know how you feel about conversions. Pi 0.011 squared velocity. So I do some math there, and I end up with a velocity of V2 equals 14.169. So that becomes my velocity right here. So that becomes 14.169 squared. And the answer, and at that point it just becomes in algebra problem. You go ahead and solve it for it. On your quest, it asks you have to convert from atmospheres to pascals, but any conversions that you'll need, we'll give them to you. Like I said, this problem won't be exactly like 21. 21 was just a good example to give you, so don't be like Ryan, be like, oh, I know how to do this. If you know the setup, and you know what they're asking you for, I feel confident that you guys should get that Bernoulli's problem correct.
Wait, so it's not gonna be like 21?
Not exactly like 21.
I guess I'm gonna ask for the same thing.
No. That's why, no, like just like the last review, it wasn't exactly the same.
The letter problem?
Well, that problem is like special. So Mr. Rios is going to do number 9 with you, and then he's going to do number 7 with you guys. You ready for the big show? No WWE references in my class.
Alright, we're gonna change up number 7 a little bit.
Do number 9 with them first.
Number 9? Alright, we'll do number 9. We're looking at Archimedes' principle here, which states what? What is Archimedes? Talk about this a little bit with you guys.
When you set an object in water, it displaces.
Right, and what do we know from that?
Isn't it the volume of the object that displaces the volume of water?
Okay, you're on the right track, right? You put an object in water, what's gonna happen to the water level?
It displaces the same volume.
It's gonna rise, it displaces some amount. So what can we say about that displaced water?
It's the same as the mass or the volume? I can't remember. The volume, right, is the same?
Well, for one, if you submerge an object fully, you know that whatever amount of water it displaces, That's the equal to the volume of the object, right? For one, that's one thing that we can tell right away, right? All right, but the second thing, what about regarding forces? What's the force that we talk about? What's that? Buoyancy, right? So what can we say about buoyancy?
It's equal to
the weight of what?
the weight of the object.
Of not the object of what? What went up?
Oh, the dead.
The displaced water, right? So the displaced water. So whatever water is displaced, okay, the weight of that, weight, not the mass, not the volume, the weight of that is equal to that buoyant force, right? Which is pushing up against that water. Okay, if you can think of that and know that, you'll be able to solve these problems pretty easy. So just by saying it. So let's look at number 9. A boat has a density of 600 kilograms per meters cubed. Its surface area is 5.7 meters squared, and its volume is 0.6 meters cubed. When a raft is placed in fresh water, to what depth? So we're going to figure out the depth of the bottom of the boat from the level of water. Okay. So as always, let's write down what we know. All right. What do we know from this problem? Density of what?
6 meters.
The boat.
Density of what though? First.
Oh, the boat.
Okay. Make sure we're specific. We're very specific on what. Write down everything you know. Okay. On one side. All right. Density of the boat. Right.
Yes.
So we'll call it the raft. So we'll put rho and then put a little r for that. Okay. So what's the density of that?
600 kilograms
600 kilograms
per meter.
per meters cubed. All right. What else?
Surface area is 5.7.
Okay. So we know the area.
5.7 meters squared.
And the volume is 0.6 meters cubed.
Okay. The volume of what though
The
specifically?
volume of the no, the width. Oh yeah, the volume. No, yeah, the raft.
If you
Raft or boat? I'll put boat. I'll put B for boat. What's up?
Don't step on my
This? This is a Greek letter, rho. Yep, the little P. All right. Okay. So let's write down the volume, right? Volume of the boat
yeah,
is 0.6
meters cubed.
Meters cubed.
meters cubed. All right. What else?
Water.
What's the density of water? It should give you this in the problem, but if you don't, it's 1,000 kilograms per meters cubed. What else? Yep, that's pretty much all you need. Okay, what are we looking for? The height. Okay, so imagine this. Okay, this is what you gotta imagine. You got the water, you got the boat. All right, this is your area right here. This is the height. So how far below the water level is what we want to find out. Okay, all right, you have the volume here. The boat, right? So we know this. We know the density. We know the area. All we got to figure out is the height of how far down it went. Okay.
Can you draw that a little bit bigger for the people at home?
Yes, okay.
And feel free to like make fun of them for not being here.
Mister, no bullies on. No bullies on.
Only random acts of kindness over here, Chief.
You don't call this review kindness?
Yeah, you're doing
You
this.
don't call me reporting that for them kindness?
Yeah, you're doing them a favor.
All right. So we got the water. We got the water. You gotta draw or imagine what we're trying to solve here. Okay. So we got the volume. We got the area of the boat underneath. And then we're looking for the height. This is what we need to find out how far it is below the level of the water. Okay, does the problem make sense? We got all we need right here just to solve this. Okay, now we know Archimedes' principle, right? That's all we need for this problem. So Archimedes' principle states that buoyant force is equal to what? To weight of what? Not the boat, right? Displaced water. Be very careful, okay? Repeat that over and over and over. Displaced amount of water is equal to that buoyant force pushing the object upwards, okay? All right, so we can say for the equation that buoyant force Okay, that force that's pushing, I'll put it in a different color. That force is pushing the object, or that it's exerting on the object, okay, it's going to be equal to that the weight, which is the force of that liquid displaced, okay? All right? So the force of the boat, of the liquid that's displaced, okay? So we're looking at that relationship there, which is just weight, okay? This is weight.
You have a question? Okay. You're just saying the weight is equal to the buoyancy force, and that's why it floats.
Okay, that force.
So that FG is the same thing as weight?
Yes. This is the weight.
Force of gravity.
Okay. All right, let's break this formula down. Okay, we're talking about forces, right?
Yes.
So, okay, so what is the force? What formula can we use for force that we know from the past already?
MA.
M what? M what times what?
A.
Good so far?
Thanks, Lars.
Can we use weight?
What's up? Can we use what? Let's try to derive this. Let's try to derive this from what we know. Okay. It's a little bit different, but
Is that just saying that
Well,
weight is what? It's mass times gravity. Okay. All right. So now we can use the densities, or the form. Let's figure out the formula for density for. Let's use density of water first. We're looking at the buoyant force, right? Using the liquid exerts on the object first.
Yeah.
So density is equal to mass over volume, right? This is for water. How can we rewrite this so that we have mass and we can put this in here?
density times volume?
Good. So if we rewrite this equation here, it would look density of water times volume, right? All right. So we can put that in there. All right. So we have density of water times volume, right? Times G, right there. Okay, but we could do the same thing for this side, right? We have mass. We're looking at weight, right? The displaced water. So we can do the exact same thing here with a boat. Okay, so rho of the boat is equal to mass over volume, right? We can rewrite this. So we have mass and that can go in there as well. Okay? All right, we all right? Now, we got one more thing that we got to look at as far as volume goes. Okay, we're looking for the height, right? The height underneath the water level. So, we know the volume of the boat. Okay, so we don't have to worry about that. But as far as the water, okay, the water level, what's the formula for volume? Area times what?
Height.
Yes, that's correct. Just area times height, right? Okay, so we know volume is area times height. So we rewrite this for height, because we're looking at the height, right? We're looking for this here. We can rewrite the equation so that we're looking for height. We know the volume, right? We know the area. We don't know the height. So all we got to do is rewrite this equation so that it looks like this. The height is equal to?
Area divided by.
No,
Height is equal to area.
Oh,
What is it
volume
gonna
divided by
What is it?
area.
Volume divided by.
8 divided by 8.
All right. Okay, now, I'm sorry. We're solving for, sorry, let's plug this in. That's my bad. My mistake. We're plugging this in for B here, right? This is what we figured out right now. All right, now we can solve for height. We move everything over, and then we put our numbers in, and that's it. Okay? So, is it kind of making sense a little bit? Okay. You just have to derive what volume is. Volume is area times height, right? So if we break this down, we know the area already. We just gotta make sure we find the height. So now, how do we solve for height here? Multiplying all these together. You just divide it. You do the opposite, right? So the density of water times the area times G.
What does the G cancel out?
Yep, it would. The G cancels out, so you end up with this formula for height. And that's it. Okay, do we have these numbers here? These variables here? Up there? So we did the physics portion, now you just put in the numbers, put it in the calculator, and you should get your height right there.
Do you cancel out the G's first?
Yeah, the G's cancel because you end up with a G on both sides anyways. Well, when you divide it over, it's going to cancel out anyways, right?
Oh, because you're trying to leave H myself, right?
All right, so what are our numbers? 600, right? For the boat. Volume of the boat is 0.6. Density of water. And the area. So you put that in the calculator and you should get your height in meters. Yeah.
Remember how you said it was different than mine?
Which one?
I'm about to kick that whole group out. Guilty by association, Dirk.
You guys get that? So, in short, you're looking at Archimedes' principle. Okay, think about what's going on. Archimedes' force, the force underneath or the exerted by the liquid on the object is equal to the weight of the displaced fluid. Okay. All right. We set those equal to each other. Then we can use. We can derive. We can find mass using the density, right? You know, density uses mass. Same thing on the other side. Okay. Once you plug in the new formulas, you just rewrite densities. You put them in there, And then one last thing for volume, this time they only give you the area, but we know the formula for volume is just area times height. You can put that in there for volume. And then from there, you just basically move everything over. So you're looking for the height, which is basically from the level of the water all the way down. Once you move everything over algebraically, then you have your new expression there. Okay.
You mind if I jump in real quick?
Yeah, dude.
Because initially what Frida wanted to do, Frida immediately wanted to set up buoyancy is equal to weight. And she knows that buoyancy is density, gravity, volume. So buoyancy equals to the weight, which is mg. And we know that m, like we established earlier in the review, m was density times volume and gravity.
Okay, let me stop you there.
Yeah, and that's exactly the connection I wanted to make. It ends up being the same thing.
You see where that comes from? No.
That's because you immediately wanted to jump to, oh, buoyancy force is equal to the weight, and I make the weight, I make my m this, and I'm like, it ends up being the same thing, except in this problem, you have to recognize that volume is area times height.
Since I just got confused earlier with the MG
So for the people that are here, again, this is you came to the review, ask questions. People at home can't ask questions, you can. All right. The last one, number 7, and then we all get to go home and eat McDonald's. Just kidding, just me.
I don't like
There's going to be, we're changing number 7. I know what I wrote, and I'm sorry people at home, but we are going to change number 7 to a different problem. So Mr. Rios will read it out. We'll read it to you how we've changed it. And I might write it on the side or something, that way.
All right, here's the problem number 7.
We're changing it. So get ready to make
It's
the
very
changes.
similar, but it just changed a few things. Okay. A block of titanium is dropped in a cup of water, and 200 centimeters cubed of water is displaced out of the cup. Okay, what is the mass of the titanium? In order to verify that it has a density of 25.0 grams per centimeters cubed.
So a block of
A
titanium.
block of titanium is dropped
Uh-huh.
in a cup
Of water.
and 200 centimeters cubed
200 centimeters
cubed of water.
cubed of water is displaced. What is the mass?
What is the mass of titanium?
So we're still on the rate, the volume.
In order to verify.
What is the titanium mass?
In order to verify that it has a
Well, let's just say
density.
titanium density is
Grams per centimeter.
Take that.
All right.
and I'm gonna put this
That sounds good.
right there. So this is the new number 7. In case you need to make some changes to it.
It's outside.
You don't get any blue off YouTube.
Not a science.
It's a really bad, honestly.
All right, what can we write down? Let's write down what we know. What do we know? What is it?
Density of water, 1,000.
Okay.
Volumes.
200.
Volume is 200 milliliters.
Well, no.
What is it, meters per cube?
What's displaced?
All right, what else?
The displacement is.
Displaced. Okay, so that's the volume, right? What?
Wait.
Volume. What else do we know?
We know. There's another number. So,
What is that other number?
is it a G? Skip over.
25. Wait, no.
The density of titanium.
This is 25.0 grams per centimeters cubed. All right, and we are asked to look for the mass, correct? The mass of titanium. All right, that's all we got. Okay. Based on what I told you earlier, we're talking about Archimedes' principle. We can say, okay, that the volume of water displaced is going to equal to what?
Is
The weight.
Okay, besides buoyancy force, what can it tell us?
the weight?
If I drop this in a graduated cylinder and it displaces 3 milliliters, what can we say about those 3 milliliters in regards to this object here? It's equal to the what of this object? The volume. Okay? The volume of the object. Okay? Very important to remember that. So if I put this in a cup of water in a graduated cylinder and I drop it and we displace 3 milliliters, then it's going to tell me that this marker is equal, the volume of this marker is equal to 3 milliliters. Okay? So I'll write that down if you want to write it down. Put people home. So the water, the Does that make sense? Volume of the water displaced equals the volume of the object. All right. So knowing that, we can use the density equation to figure out the mass of titanium. We are given the density, okay? We are given the volume displaced, right? So all we have to do is rearrange this to find the, what are we looking for? Mass. So
Yeah.
if we rearrange it algebraically, we should end up with mass is equal to, right? All we do now is we put in values. This cancels, and we end up with what? 5,000?
Titanium's heavy.
Grams.
Those are grams.
Okay, it is in grams. Careful with the units, okay? The problem gives you something in kilograms, make sure, and the density is in if the density is in grams per centimeters cubed, and the problem gives you an object in kilograms, make sure you keep them all the same, and convert accordingly. Okay, make sure you keep the, that's why we write everything down, write the units so that you can see the units, make sure they all match up. That's it. That's all there is. I don't know if you want to add anything else.
Yeah, one quick thing. You have to understand this idea of Archimedes' principle first. The volume of the water displaced is going to be equal to the volume of the object. You have to understand that in order to really understand why this volume is equal to that other volume. Like, why am I solving for this volume if they're asking me for that other thing? Because they're the same volume. When something's submerged, the volume of that object is equal to the volume of the water displaced. So know Archimedes' principle, and then now you can like density equals mass divided by volume. Our big warning is that if you do badly on the test, please do not blame the review, because these problems are meant to guide you, not to give you the exact problems.
Disclaimer.
Yeah.